Okay, so we left off lecture on Monday by setting up this example. Just to remind you, the question states that we have a physics student standing on the edge of a cliff, throws a stone vertically downward at 10 meters per second, and the instant before the stone hits the ground, it's traveling at 30 meters per second. So let's go ahead and add that piece of information. So the stone is traveling at 30 meters per second right before it hits the ground. And then the same student with the same stone throws the stone vertically outward, not vertically outwards, horizontally outward. So instead of throwing it down, throwing it horizontally outward, and it follows some trajectory. And the question wants to know what is the magnitude of the velocity when it's about to hit the ground. So let's go ahead and set that up. We have follows a trajectory like this, and it has some v final, and we want to know the magnitude of that v final right before it hits the ground. So I've suggested to split this problem up into two parts. Part one is we really need to figure out how high this cliff is. Then we can figure out if you throw a stone outward, what velocity is it going to have when it right before it hits the ground. So figuring out the height of the cliff, we'll go ahead and copy this part of the situation because we're going to use that to figure out the height of the cliff. Okay. So setting up the problem in the coordinate systems, in the coordinate system that we stated in class, meaning x this way, y this way, and origin here, let's start by identifying v initial y is negative 10 meters per second. We know v final y is negative 30 meters per second because that was given. And notice that when I write these quantities in my coordinate system, I identify the fact that going downward is negative, so I need to call this a negative velocity and a negative velocity. Now, if I know initial velocity, final velocity, I also know acceleration due to gravity in the y direction is just minus g, or negative 10 meters per second squared. By the way, we are going to use negative 10 in this problem rather than 9.8. It's not stated, but I've made that choice. Now to figure out delta y, the equation that's going to help us get there is v final y squared is equal to v initial y squared plus 2a delta y. So plugging everything in, well, before we plug everything in, let's symbolically solve for delta y because we know that's what we're looking for. So we know delta y is equal to v final y squared minus v initial y squared all over 2a. And now plugging everything in, we get negative 30 meters per second squared minus negative 10 meters per second squared, all divided by 2 times negative 10 meters per second squared. Okay, if we plug all this in, let's see what we get. We get basically negative 40 meters. So delta y is negative 40 meters. Okay, so we know how high the cliff is. The cliff is 40 meters tall. Now to solve the second part of the problem, we're going to use the height to figure out how fast this ball is moving, right, or this stone is moving right before it hits the ground. So for that part of the problem, I'm going to go ahead and use this picture since that's our setup. So we have, now the added information is basically the fact that this is 40 meters. Okay, the fact that that's 40 meters, we need to work with the x and y direction separately. So x direction here and y direction here. In the x direction, we know v initial x is 10 meters per second. They tell us that the stone is being thrown horizontally outward at 10. And since that's our positive direction, that's positive 10. We know that for all problems of projectile motion, unless stated in the problem, we're going to ignore any acceleration due to drag or air resistance. So acceleration in the x direction, 0. if you know acceleration in the x direction 0, you know that the velocity stays constant. So v final x is also 10 meters per second. So really, our x component is pretty much already done and solved. So let's work on the y component. V initial y. Well, when you throw something outward, you don't give it any initial velocity in the y direction. Basically, it's the same as dropping it in the y direction. So when we throw something horizontally outward, its initial velocity in the y direction is 0. It's falling under the effect of gravity, so acceleration is minus g. And we know that the delta y it's going to travel is negative 40 meters, because we know when it ends up here, it's traveled down 40 meters, because that's exactly what we solved for in the previous problem, was the height of the cliff. So using that information, we can go ahead and solve for the v final y. So v final y squared equals v initial y squared plus 2a delta y. Same equation as before, but this time we're solving for v final y. V final y is equal to basically the square root of 2a delta y. All right, let's plug everything in. V final y is equal to square root of 2 times, and also we get a plus or minus, because when you square root both sides, you get two possible solutions. So v final y is 2 times negative 10 meters per second squared times delta y, which is 40 meters. All right, let's crunch these numbers, and we should get that v final y is plus or minus about 30 meters per second. Oh, oops, not 30 meters per second. My apologies. This should turn out to be about, let me just calculate it. So we have 2 times 400, so 800, and square root 28.28. So about 20, well, I'm going to go ahead and carry 28.28 meters per second around once we get to the end. So if we know a note, this is plus or minus. So we need to choose, depending on the problem, which solution we're trying to look for here. So if the stone is traveling in this direction, the y component of its velocity, we expect it to be negative, and the x component we already solved for. So it's the negative solution, really, that is the final velocity here. So the v final y here is, in fact, negative 28.28 meters per second. Now, the last thing we're left to do is finding the magnitude of the velocity when right before it's about to hit the ground, because it didn't ask us for the vector. It specifically asked us for the magnitude. So I'll write the vector first. So v final y is equal to 10 I hat minus 8 j hat meters per second. And the magnitude of v final y is equal to square root of 10 squared plus 28.28 squared, which gives us about 30 meters per second. So the magnitude of the velocity is actually also 30 meters per second. Now, some of you might find this kind of surprising. So if you throw the stone downward at 10 meters per second, right before it hits the ground, it's moving at 30 meters per second. But even if you throw the stone outward, not down at all, it's still moving. It's the magnitude of its velocity is 30 meters per second. And some of you might not find this surprising at all. If you have covered conservation of energy in high school physics, you might actually be able to defend why it needs to be 30 meters per second. Okay, so that was the projectile motion example from class.